Hello everyone, welcome to this lecture. Just a quick recap. In the last lecture we saw various examples of countably infinite sets. So we will continue the discussion on countably infinite sets, and the plan for this lecture is as follows. In this lecture uh, we will see several other examples of uncountable sets, and we will discuss about Cantor's diagonalization argument and Cantor's theorem. So as I said earlier, in the last lecture we saw examples of several countably infinite sets, and the nice thing about those sets is that their cardinality is same as the set of positive integers, right? So we saw several such sets, namely the set of integers, the two-dimensional integer plane, the set of rational numbers, the set of prime numbers, set of all binary strings of finite length, and for any finite alphabet, the set of all possible strings of finite length over that alphabet. So it might look like that every infinite set, somehow we can show that its cardinality is same as the set of positive integers, right? But interesting part here is that that's not the case, and the focus of this lecture is to argue about the existence of about the existence of infinite sets whose cardinality is different from that of a set of positive integers. Okay, so we begin with our first set, namely the set of all binary strings but of infinite length. Okay, and this set is denoted by this notation 0 1 raised to power infinity. So some examples of binary strings of infinite length, if I consider the string x equal to 0 0 0 0 and a sequence of zeros which never ends, then that's a binary string whose length is infinite. Its length is infinite because the characters in this string will never end. Similarly, if I consider this binary string where I have alternate zeros and ones and a sequence goes forever, then that is again an example of a binary string which has infinite length. Similarly, if I consider this binary string consisting of zeros and ones where at the nth position the bit is 1 provided n is a prime number, otherwise the bit is 0. So for example, 1 is not prime, so that's why at the first position I have the bit 0, 2 is prime, the integer 2 is prime, so that's why at the second position I have bit 1. The integer 3 is a prime, that's why at the third position I have the bit 1. Integer 4 is not a prime, that's why I have at the fourth position the bit 0, and so on. So again, this is an example of an infinite length binary string. Okay, so before proceeding further, you might be wondering, is there any difference between the set of all binary strings of finite length, namely the set 0 1 star, and the set that we are considering right now, namely the binary set of binary strings of infinite length? It turns out that indeed these two sets are completely different. The difference is in terms of the length of the strings in the individual sets. Okay, so when it comes to the set of first of all, both these sets has infinite number of strings, remember that. Okay, even if I consider the set 0 1 star, right, the number of strings in that set is infinite. However, the length of each string in that set will be finite. Okay, so the primary difference between the two sets is the following. If I consider the set 0 1 power infinity, then the property of this set is that the length of any string in this set cannot be bounded by a natural number. Okay, because you take any string in this set, we can never say what will be the end digit or end bit of the string, because the sequence of characters in each string in this set will be an infinite sequence. Okay, whereas if I consider the set 0 1 star, then the property of this set is that each string in this set is of finite length. That length might be arbitrarily large, it might be enormously large, positive number, but it is a bounded quantity. That means we will know that it starts with certain bit and it ends with a certain bit. It's not the case that its end bit is not known. So that's the primary difference between these two sets. Okay, so that's why you can see here in the examples that I have listed down, we don't know what exactly is the end bit of these strings. That's why we have dot 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 written down here. So now what we are going to discuss is a very beautiful result, a very fundamental result attributed to Cantor. It's called the Cantor's diagonalization argument. And using this diagonalization argument, what we are going to prove is that the set of all binary strings of infinite length is an uncountable set. That means we cannot enumerate out, we cannot list down the elements of this set. Okay. So the proof will be by contradiction. Okay, we will use a proof by contradiction mechanism here. So we are supposed to prove that this set is an uncountable set, but we believe contrary, we assume the contrary, and we assume that this set is countable. And if it is countable, then it must be having a sequencing of the elements of the set. So imagine that a sequence is this R1, R2, Rn and so on. That means we know that what is the first element in this set, what's the second element in this set and so on. Right? So remember, each element in this set 0, 1, infinity, 0, 1 raised to power infinity is a binary string of infinite length. So imagine R1 is of this form. Okay, it has first bit being D11, second bit is D12, third bit is D13, fourth bit is D14 and so on, right? And it's an infinite length string because it's a member of the set 0, 1 raised to power infinity. Similarly, imagine that the bits of the string R2 are D21, D22, D23, D24 and so on. Similarly, the bits of the string R3 are D31, D32 and so on. Okay. And since the sequence is an infinite sequence because there are infinitely many elements in this set, this list of elements of the set 0, 1 star will go on. That's why I have dot 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 here. Okay. Now what I am going to do here is I have to arrive at a contradiction. The way I am going to arrive at a contradiction is that I will show that there exists at least one string which is of infinite length and which is binary and which is not there in this sequence of binary strings that we are assuming exist, right? So we are assuming that we have a sequence R1, R2, Rn and so on, and that sequence is the enumeration of all the elements in the set 0, 1 power infinity. But what I am going to show is I am going to show the existence of one string which is going to be missed in this sequencing, which will show that the sequencing which we are assuming to exist does not exist actually. So what exactly is that string? So you consider the binary string R, okay, which is obtained by focusing on the bits along the diagonal here. So remember, this diagonal is an infinite diagonal because I have more elements to follow in this sequencing, and I am just for R4 I will consider D44 and so on. So I am considering the diagonal binary string. It's an infinitely long binary string, and what I consider here is now I consider a new string which I denote as R bar, and R bar is obtained by complementing each of the bits in this diagonal binary string, right? So if D11 is 0, I take its complement, so that is denoted by D11 bar and so on. Now my claim is that this string R bar which I have constructed here, which I am considering here, definitely it's a member of the set 0, 1 power infinity. Why? First of all, it's a binary string, okay, and its length is infinity, right? Because the diagonal here which I am considering here, the diagonal binary string, it's of infinite length. So the complement of that string also will be of infinite length. So definitely R bar is a member of the set 0, 1 infinity. But the interesting thing here is that the string that the string R bar that I am considering here will be different from all the strings R1, R2, R3, R4 and so on in the sequencing which I am assuming to exist. So you can verify that. Okay, so if I consider the first string R1 in my list, R bar is definitely different from R1 because the first bit of R bar and first bit of R1 are different. They are complement to each other. Similarly, if I consider the second string R2 in my sequencing, it will be different from R bar because the second bit of R bar will be different from R2, right? And this process will continue. You take any string in the sequencing which you are assuming, there will be at least one bit in that string in the sequencing which will be different from the corresponding bit in R complement or R bar. So that shows that the sequencing that we are assuming is not the complete sequencing of the set, or it's not the complete sequencing of the elements of the set 0, 1 power infinity. We are definitely missing some elements from the set 0, 1 power infinity which we are not writing down. And that shows that your set 0, 1 power infinity is an uncountable set, because as per the definition of a countably infinite set, if the set is countably infinite, there must be some valid sequencing, some sequencing of the elements of that set. So it doesn't matter what is the sequencing. If you show me any sequencing for the set 0, 1 power infinity, I will show you the existence of one string which will be missed in that sequencing, which shows that no sequencing of the elements of the set 0, 1 power infinity is possible. Okay. So there are few subtleties involved here when running the Cantor's diagonalization argument. It might look to you that why can't I run the Cantor's diagonalization argument to even prove that the set 0, 1 star is also uncountable, right? So 0, 1 star, remember, it's a set of all binary strings. There will be infinitely many elements in the set 0, 1 star, but the length of each string in this set will be finite. So let's see where exactly the Cantor's diagonalization argument fails when we try to run it for 0, 1 star. So we will start assuming that we have a sequencing for enumerating out the elements of the set 0, 1 star, where the listing is say R1, R2, Rn and so on. Okay. So again, I will focus on the individual bits of R1, R2, R3 and so on. The important point here to note is that since each of the strings R1, R2, R3 are the members of the set 0, 1 star, their length will be finite, right? So I will know that d1i is a bit, and I will know that I is actually some number, some natural number, some positive number. It's not the case that the bits of R1 will keep on going forever. In the same way, if I consider the string R2, I know j is a natural number. Okay, so sorry for the typo here. This should be d2j. Okay, and similarly this should be d3k and so on. So when I consider the bits of the string R2, I know that the length, there are finitely many bits in R2. That means j is a natural number. Similarly for R3, I know there are finitely many bits in R3. That means k is a natural number and so on. However, the number of elements in the set 0, 1 star is infinite. That's why this sequencing will keep on going forever. So now, as per the Cantor's diagonalization argument, I will consider the binary string R complement, which will be the complement of the diagonal string here. So the diagonal string will be like this. Okay, and it will continue forever. Definitely R bar that I have constructed here will be different from each of the strings R1, R2, Rn in the sequencing, provided the bits of R complement or R bar continue forever, right? That means only when R bar goes forever, that means the bits of the R bar keeps on going and going and going, never ends, then only I can claim that R bar is different from each of the strings R1, R2, Rn in my sequencing. But notice that if that's the case, then the string R bar which I am constructing here is not an element of 0, 1 star. This is because if at all r bar belongs to 0, 1 star, then its length has to be finite, right? I can't say that the bits of the string r bar continue forever. That is the characteristic of a binary string which has infinite length. But if at all r bar is of finite length, right, that means it has to stop somewhere. And if it is of finite length, definitely it will be appearing somewhere in my sequencing. And that's where the Cantor's diagonalization argument fails. Whereas when we considered the argument for the set 0, 1 power infinity, there was no restriction on the bits of r bar. It was allowed to go forever. So that's the point where the Cantor's diagonalization argument fails when we try to run it for the set 0, 1 star. Let's see another subtlety to make my point more clear. So let's try to see whether we can run the Cantor's diagonalization argument to prove that the set of integers is an uncountable set. Remember, it's a countable set, and we had shown sequencing. We know how to sequence or list down the elements of the set of integers. So as per the Cantor's diagonalization argument, the proof will be by contradiction. So I will assume that I have a sequencing for listing down all the integers. So let r1, r2, r3, rn be the elements in the sequencing. And then each integer, right, can be considered in terms of the its decimal representation, namely the digits that we have in that integer. Right, so imagine that digits of r1 are d1, 1, d1, 2, d1, 3, d1, 4, d1, I. Namely, r1 has I number of decimal digits. Similarly, say r2, the integer r2 has j number of decimal digits. So again, sorry for the typo here. This should be d2j. And similarly, assume that r3 has k number of decimal digits and so on. Right. Again, remember, each integer has a magnitude, and when I say it has a magnitude, that means it's possible only when the number of digits in an integer is finite. You can't have an integer which has infinitely many digits in its decimal representation. That's not a valid integer at all, because you don't know what exactly will be the magnitude of that integer. So each integer will have finitely many digits. That might be arbitrarily large, that's a different thing. And the number of elements in the set of integers, that might be infinite. That's also fine. But the property is that the length or the number of digits in each integer will be finite. So again, if I consider the diagonal digits here and flip them and obtain a new string of decimal digits, say r bar, then I can say that r bar is different from all the integers in my sequencing, provided the digits of r bar continue forever. Then only I can say r bar is different from r1 and r2 and r3 and r4 and every integer in my sequencing. But if that's the case, that means if I allow the digits of r bar to continue forever, then that's not a valid integer, because every integer has to stop after certain number of digits. That might be enormously large quantity, but it has to stop somewhere. I can't have an integer whose digits continue forever. So the resultant sequence of digits r bar, which I will construct as per the Cantor's diagonalization argument, will not be a member of the integer set. So I am not getting a contradiction that I now have a new integer which is not there in my sequencing. Right? In the same way, I can't run Cantor's diagonalization argument to prove that a set of rational numbers is uncountable. Remember, the set of rational numbers are countable even though it's an infinite set, and we know how to enumerate or list down the elements of the set of rational numbers. So again, let's see where exactly the Cantor's diagonalization argument will fail for the set of rational numbers. So we will assume that we have a sequencing or listing of the set of rational numbers, and let r1, r2, r3 be the rational numbers, listing of the rational numbers as per my sequencing. Okay, so again, what I have done here is I am not focusing here in my sequencing, I am not focusing on the decimal point. Okay. That is just for simplicity. I am focusing on the remaining whatever is appearing after the decimal point in the decimal representation of your rational numbers. I am focusing only the digits here. I am not focusing on the decimal point here, right? That is just for simplicity. So again, uh, the digits of the first real number, or the digits of the, sorry, not real number, the digits of the first uh, rational number, I am assuming them to be d11, d12, d13, d14, and so on, right? So now in this case, what's happening is the number of digits in the decimal representation of any rational number might be finite, or it might be infinite. It might be finite in the sense it terminates after some point. Say for instance, if I consider the rational number, say 1 over 2, then 1 over 2 is 0.5. So it terminates somewhere. But 0.5 I can imagine as 0.5000000 followed by infinite number of zeros. So even if the decimal representation terminates after certain positions for the given rational number, I can imagine that I can append it by infinite number of zeros, and hence the number of digits continue forever. Whereas I may have a rational number whose where in the decimal representation the number of digits never terminates, but it will have a never-ending periodic recurring digit sequence, right? So for example, if I consider the rational number 1 over 3, then 1 over 3 is 0.33333333333. It never terminates, right? So that means when I am writing down the decimal representation of the rational numbers in my sequencing, I can imagine that for every rational number in its decimal representation, the digits continue forever. But if it even if it terminates, it continue forever, or it does not terminate, but in that case it will be a never-ending recurring sequence. It won't be a case that it does not terminate and simultaneously it does not recur. That won't be the case for a rational number. If at all the the digits does not terminate, then it will be definitely recurring somewhere, right? So now again we will focus on the digits along the diagonal entries here, and we will flip them. We will flip them in the sense that what you can imagine is that d11 complement here represents any digit different from d11, right? So for the notion of complement makes sense in the context of binary strings here. So, but we can generalize it here and assume that d11 complement represents any digit different from d11. Similarly, d22 complement represents any digit different from d22, and so on. So that will be a new sequence, a new string of decimal digits which we have constructed here. Definitely, this new string of decimal digits which we have constructed will be different from all the sequence of decimal digits in your sequencing, provided the digits of this R bar continue forever, right? Now the question is, can I say that this R bar definitely is a rational number? Only in that case I can arrive at a contradiction. But the point here is that there is no guarantee that the sequence of digits, right, in this string R bar has a periodic recurring digit sequence, right? So what I'm saying is that it may be possible that in R bar you have a non-recurring sequence of digits. That means even though the sequence of digits does not stop, you do not get any recurrence or any periodic recurrence of the you don't get any occurrence of periodic recurring digit sequence in R bar, right? That means this R bar need not be a rational number, right? Because we don't know whether all these digits D11 complement D22 complement D33 complement DNN complement they are distinct or they are going to be repeated, right? We don't have any guarantee whatsoever. So that's why we don't get a contradiction. We don't get the guarantee that this string of digits R bar represents a rational number. It may represent a irrational number. So for instance, if you consider root 2, which is an irrational number, then you know that if I consider the decimal representation of root 2 and if I focus on the sequence of digits and the decimal representation of root 2, then it's a never ending sequence and you don't have any recurring or any periodic recurring digit sequence in this sequence of decimal digits. So your R bar may be a sequence like this. You don't know, right? So you can't say that R bar that you are obtaining here is definitely a rational number. So again, Cantor's diagonalization argument fails if I try to apply it to the set of rational numbers. Okay. So now we know at least one set, namely the set 0, 1 power infinity, which is not countable. Now we will see some other sets as well which are not countable. So what we are going to show here first is that a set of real numbers excluding between 0 and 1 but excluding 0 and 1 is uncountable, right? So that set is denoted by 0, 1. So this is the representation of the set of all real numbers between 0 and 1 excluding 0 and 1. So how I am going to show it is uncountable? Well, we had already shown that the set 0, 1 raised to power infinity is an uncountable set. I will show you now a bijection between the set 0, 1 power infinity and the set of all real numbers between 0 and 1. That will automatically show that conclude that the set of all real numbers between 0 and 1 have the same cardinality as the set 0, 1 power infinity. Okay. So what is the bijection? The bijection is very simple. So if I take any x in the sets or any real number between 0 and 1 excluding 0 and 1, right, that will have a binary representation. So let the binary representation of that real number be 0 point y, where y is a binary string. Okay, so what will be the function f? The function f of x will be y. That means I will just chop off the 0 here and the point here and just I will focus on the binary representation, that means the bits in the representation y, and that will be the mapping of x as per the function. So how exactly this function will look like? So if you consider, say for instance, x equal to 0.5, okay, so the mapping of 0.5 will be the binary string 1 followed by infinite number of zeros. Why? Because 1 over 2 in binary can be represented as 0.1 and I can always put infinitely many zeros even though 1 over 2 is 0.1, right? So this will be my y, and that's why f of x will be mapped to, I chop off this 0 at this point. Okay. In the same way, if I consider x equal to 1 over 3, then 1 over 3 can be represented as this infinite sum, 1 over 4 plus 1 over 6 plus 1 over 64 and so on, right? This is an infinite sum and it is in a geometric progression. If you apply the rule of the summation of infinite geometric series, you will get that this sum is nothing but 1 over 3. But now if I focus on the binary representation of 1 over 4, 1 over 16 and so on, so this will be the binary representation. So anything after the decimal binary point here will be my y. So I will chop off this 0 and this, and that's why my x will be now mapped to this y and so on. So it's easy to see that this function f is indeed a bijection. I am leaving that as an exercise for you because the simple fact is that if you take any x in any real number, it will have a unique binary representation. That's all. That's a simple observation here. Now if I consider the set of real numbers, this set R denotes a set of real numbers, okay, then it contains the subset 0, 1, right? It has all the, it also includes all the real numbers between 0 and 1 also. And since 0, 1, the set of all real numbers between 0 and 1 is uncountable, and remember we had argued that if you have a set with a subset which is uncountable, then the whole superset also will be uncountable. So that automatically shows that a set of real numbers is also uncountable. And intuitively, the main reason that a set of real numbers is uncountable is that it has irrational numbers as well, which we can't enumerate out. So Cantor proved a very interesting result as well. He showed that you take any set A, then the cardinality of that set is strictly less than the cardinality of its power set. So remember, the notation P of A denotes the power set of A, where the power set is the set of all subsets of that set. So of course this statement is true if your set A is finite, namely if your set A has n number of elements, then its power set will have 2 to the power n elements, and we can always prove that n is always strictly less than 2 power n. Okay. Now what if A is an infinite set? Can we conclude that this theorem is true even for an infinite set? And Cantor showed yes. So the proof again is by contradiction, and we will run the diagonalization argument here as well. So we will assume that let the cardinality of the set A be greater than equal to the cardinality of its power set. Now before proceeding, a quick fact which we will be using in this proof is the following. If you have sets x and y, and if the cardinality of x is greater than equal to the cardinality of y, then there always exists a surjection from the set x to y. This is a very simple fact which you can prove very easily, so I am not going into the proof of that. We are going to utilize this fact in this proof. So I am assuming here that the cardinality of A is greater than equal to the cardinality of its power set. That means there will be some surjective function from the set A to the power set of A. I don't know what exactly is the structure of that surjective function, but I denote that surjective function by f. So now what I have done here is let the elements of A be x1, x2, x3 and xn and so on. Okay, it's an infinite set, right? So there are infinitely many elements. So I am assuming that the elements of the set A can be listed down as x1, x2, x3 and so on. And I have listed down f of x1, f of x2, f of x3 and so on. So each of this f value is nothing but a subset of the A set. That means it will be an element of the power set. So depending upon which elements from the set A are present in f of x1, accordingly I have put the entries zeros and ones, right? So for example here I mean to say that f of x1, it is a set which does not have x1, it does not have x2, but it has x3 and so on. Similarly, f of x2 is a subset which has x1, it has x2, it has x3. Okay, right? So that's the interpretation of the zeros and ones in this table. Similarly, f of x3 is a subset which has x1, which has x2, but it does not have x3 and so on. Now what I am going to show is, since I am assuming that a function f is a surjective function and I have to arrive at a contradiction, right? I will show that this f actually does not exist. And how do I show that f does not exist? I have to show that f is actually not a valid surjective function. To do that, I will show you a subset which belongs to the power set, right? Namely, I will show you a subset of the A set which do not have any preimage. That means it will be different from f of x1, it will be different from f of x2, it will be different from f of any xi, which shows that the set S, the subset S, do not have any preimage, hence contradicting that the function f is a surjective function. So how do I construct that subset S? Again, I run the diagonalization argument. So I focus on the diagonal entries here. and the elements of my set S will be constructed depending upon the diagonal entries. So in this example, so the first diagonal entry is 0. So I will include x1 because here the entry is 0, so I will flip it and I will make it 1. That means I have to include x1. The second entry is 1 along the diagonal, so I will flip it and I will make it 0. That means I have to exclude x2. The third entry along the diagonal is 0, so I will flip it and will make it 1. That means I have to include x3 and so on. So that's the way I have constructed the set S here. Okay. So now you can check here that indeed the set S that I have constructed will be a element of the power set because it's a subset. It will have some of the elements from the A set, right? I'm not taking the elements in the S set from outside. So that's why it will be an element of the power set. But you can check here that S will be not equal to f of x1. That means the set S will have at least one element which is not there in f of x1. So for example, x1 is present in S, but x1 was not present in f of x1. Similarly, the set S will be different from f of x2. Why? Because f of x2 has x2, but I have not included x2 in S. Similarly, f of x3 will be different from the set S. Why? Because f of x3 do not have x3, but I have included x3 in S. So the way I have constructed the set S, it will be different from the image f of x1, f of x2, f of x3 and so on. That means S will not be the image of any xi, and hence S is not a valid surjective function. That means whatever I assumed here, namely I assumed the existence of a surjective function from the set A to its power set, which is not a valid assumption. And this is not a valid assumption because I made here a wrong assumption that the cardinality of the set A is greater than equal to the cardinality of its power set. So that means indeed the statement in this theorem is a correct statement. So what's the implication of the Cantor's theorem? It has a very beautiful implication. So this is the statement of the Cantor's theorem. So if I apply it over the set A being the set of positive integers or the set of natural numbers, then I obtain the fact that the cardinality of the set of natural numbers is strictly less than the cardinality of its power set, right? That means the cardinality of the set of natural numbers is LF null, but what I'm showing here is that its LF null is strictly less than the cardinality of the power set of the natural numbers. That means the power set of the set of natural numbers is uncountable. Now, if I treat the power set of the natural numbers as the set A, then the power set of this power set will have more cardinality. And this process will keep on going forever, right? So what basically Cantor showed is that there are infinite number of infinities. You don't have only one infinity. So LF null is one of the infinities. It's one of the infinite quantities. But you can have now infinite number of infinities because now you have an hierarchy of infinite quantities. So that's a very interesting fact about the cardinality of infinite sets. So that brings me to the end of this lecture. Just to summarize, in this lecture we saw some uncountable sets, and we proved that those sets are uncountable by using Cantor's diagonalization argument. Thank you.